All right, let's take a look at the next section in your book. This is section 9.2, adding and subtracting rational expressions. Now, I'm sure you're aware of the fact that adding rational expressions is more complicated than multiplying. And the reason that is because we have to get a common denominator. So let's quickly review how that would look. All right, so here's a simple arithmetic problem, and we're going to apply these same rules to talking about ones with variables. I need a common denominator, and sometimes the common denominator happens to be just the product of these two. And I can see that both of these go into 35. So I'm going to make my common denominator 35. I'm going to put my sign up on the top. And then I ask that question, what did I have to do to get from here to here? Well, I had to multiply by 7. So if I multiply the denominator by 7, I got to multiply the numerator also by 7. So that's 14. And I go over here, what did I have to do? Well, I had to multiply the denominator by 5. So the numerator also has to get multiplied by 5. So that's now 20. Now, if the common denominators exist, then we just go ahead and combine those two. They have the same number of pieces, 35 pieces in each of these pieces of pie here. 14 plus 20 is 34. So I move the plus sign to the top because in essence we're really combining the tops and the bottoms just kind of slide together. Now this is a situation where the denominators, the common denominator can be found by multiplying the two numbers together. That's not always the case. Let's try something else. All right, here's a pretty easy one. Sometimes the common denominator happens to be one of the numbers because they both go into, so 5 goes into 10 and 10 goes into 10. So the common denominator is pretty simple, and in this case we don't have to change this one on the right, but we do have to change the one on the left. 5 goes into 10 twice, so I multiplied by 2 to get there, so the top will have to multiply by 2 also. So that's not a times, that's supposed to be plus sign here. Here we go. So I end up with 11 tenths. We're adding these together to get a common denominator. Now there's a third thing that can happen. Usually it's the more complicated of the three. All right, here's a problem. I put a subtraction sign in here because the rules basically are the same thing. Rather than just slide the subtraction sign to the top, you could think to yourself, well, subtracting this fraction on the right is the same as adding a negative. So I could just say this is adding a negative. And the reason I do that is because the numerators are the ones we really want to make sure have the right signs. All right, so we need to ask the question, what common denominator will work here? And 12 and 15, I can see that it's 60. But let's do this in a way that make sure we can do it with even bigger numbers, because you're going to get some that are going to be challenging. We're going to use that process called prime factorization. And if you recall, prime factorization is where you pick a prime number and divide it in there. 2 goes into 12 6 times, so that's not prime, but 2 goes into 6 3 times. And when all the numbers on the outside are prime, you write it this way with the exponent. Let's do the same with 15. 3 is a prime number. It goes into 15 5 times. And that's 3 times 5. So now this is actually helpful for some problems because the numbers get so big that it's kind of hard to tell what to do. Now how do you find the common denominator, the least common multiple? Here's the rule. You take the highest degree of every base, but only take it once. So look at 2. 2 squared. 3. 3 to the first, but only take it once. And 5. 5 to the first. Only take it once. And I end up with 4 times 3 times 5, or that is 60, which is what we knew it was anyway, but that's the process. Take the highest degree of every base, but only take it once. So now I'm going to come up here and I'm going to write that fraction over. Before I actually do any of the work, I'm going to make sure I put all my signs in there correctly so I don't lose anything. All right, to get from here to here, I had to multiply by 5. 12 goes into 65. So 5 times 5 is 25. 15 times what gave me 60? Well, it was times 4. So negative 8 times 4 is a negative 32. Now these fractions are now equivalent fractions with common denominators. And so we can add them together. I'm saying add, but that's because that's really what we're doing. Also, you notice I have this minus sign right above the line here that tells me that it's inside that parentheses there. 25 minus 32, we'll see, that would be a negative 7 over 60. And guess the numerators get combined and the denominators, the numerators get added and the denominators just get combined together. All right, let's take a look at a little harder one. All right, here's one where we got 3 numbers and we got to find the common denominator, the least common multiple. Let's pretend that each of these was the denominator of a fraction, and we have to find the common denominator. Well, the variables here are actually quite easy. It's the numbers that are going to be challenging for us. But what we're going to do is we're going to look at each variable and find the highest degree of every variable, and we're going to write it down, but we're only going to list it one time. I'm only going to pull it one time. I got r squared here, and I got r to the third. Highest degree here is r to the third. So I'm going to pull that out. I got s to the fifth, s to the first, s to the third. S to the fifth is the highest, so I'm going to take that one. And I've got t squared and t. Well, t squared is the highest. Take the highest degree of every variable, but only take it one time. Now, to get the least common multiple of these 3 numbers, I'm going to go over to the side here and use prime factorization. Picking a prime number into 18, 2 goes into 18, 9, and 3 goes into 9, 3. So this is 2 times 3 squared. Hang on to that one. Take 24. 2 goes into 24, 12. 2 goes into 12, 6. 2 goes into 6, 3. This is 2 to the third times 3. Hang on to that. Let's go over here to do the last one. 15. Well, let's see. 3 goes in 15. 3 goes in 5 times. So I got 3 times 5. Now, I've got these 3 items, 1, 2, 3, and I want to take the highest degree of every base. Well, here's 3 squared, and 3. I want 3 squared, that's the highest one. I've got 2 and 2 cubed. I want to take the highest one, that's 2 cubed. And I've got 5. So this ought to be my least common multiple. Could I have multiplied all 3 of those numbers together? Absolutely, but I would have had a number way bigger than necessary. What do we got here? Well, this is 8 times 9 times 5. There's 40. 40 times 3, or 40 times 9 is 360. So my least common multiple is 360. Now, it took quite a bit of work here. Usually the numbers are the part that take the most energy. But using prime factorization is not something I do all the time. But it uses the same principle. Take the highest degree of every factor, but take it only once. All right, let's look at something else here. All right, let's take a look at these 2 polynomials here. Let's pretend for a moment that these were denominators. And we were going to add something together, and they were both denominators. So that was a denominator here, and that was a denominator here. And I want to get a common denominator so that I can add them together. Now, in order to do that, I'm going to have to use the same principle we used before. Take the factors, the highest degree of every factor, but take it only once. Well, maybe this thing factors. Yeah, in fact, it does. I can take a p out, and I'm left with p squared plus 5p plus 6. And it looks like that even factors further. This is p plus 3 and p plus 2, right? Yeah. And this over here does factor as well. This is p plus 3 times p plus 3. Oh, I can write that p plus 3 squared, and I'm doing so to get a higher power, to get a power here. Now, I want to take every factor here the highest degree of every factor, but take it only once. So I've got a factor of p. I've got p plus 3 here and here, but this is highest degree would be p plus 3 squared, and then p plus 2. So this is our common denominator. If we had to get a common denominator to add these two together, this would be it. Okay? All right, let's go ahead and actually add these two fractions together. Now again, you've got to have the common denominator. So we're going to try to figure out what's in common on the bottom. We're not going to concern ourselves right now with the numerators. We'll get to that in a second. As I look at the highest degree of every variable, I see that there's x to the first. So the common denominator is going to have an x on each of these. It's got y squared is the highest degree. And now we still need to figure out what the highest degree of these two would be. So I'm going to go over here and do prime factorization again. This is 3 times 5, and 18 is 2 times 3 times 3, 2 times 3 squared. So here I've got 3 times 5 and 2 times 3 squared. Take the highest degree of each factor. Well, that's 2 and 3 squared and 5. I'm not going to state the 3 twice. So I've got 2 times 9 times 5, or 10 times 9 is 90. 90. So 90 is going to be that number. That's the hardest part to find on these usually. Okay. Now we're going to ask the question, what did we have to do in order to get the numerator the same? We've got to multiply the top and the bottom by the same number. So if I multiply that numerator by the same thing I multiplied the denominator by, I'll get equivalent fractions here. Well, what's missing from y squared to the new denominator? Well, x is missing. So I had to multiply by x. And 15 times what gave me 90? Well, it looks like it's 6. 6 times 15 is 90. So I'm going to multiply the top 7x also by 6x, and I get 42x squared. 42x squared. Now how do you get from here to here? Well, let's see. X was the same. Y, I had to multiply by a y. Y to get times y gave me y squared. And then 18 times what gives us 90? Well, I think that's 5, isn't it? 5 times 18 is 9. Yeah, it's 5. So we're going to multiply the top also by 5y, and that gives us 5y squared. Now we have a common denominator, and we can combine these two in a single denominator now, and combine the two on the top. However, there's no like terms up there, so we can't really do anything to add them together. We're just going to write them both separately here. Okay? There you go. So it's the same process we use in working with regular, fractions, just regular arithmetic. But now you've got to just be careful that you're multiplying the top and the bottom by the same item. Let's look at a little harder one. All right, let's take a look at this. We need a common denominator. One of the first things you need to get kind of keyed in on is the fact that this is a subtraction problem. That means you're really subtracting the items on the top, both of them. So at some point, we're going to have to distribute that negative in to both terms and just change this to an addition problem. Now we can do it now, we can do it later. I'll just do it later. But bear in mind that whenever you're subtracting, the numerator is going to possess that new sign. It possesses the new sign up here. All right, we need a common denominator. So let's take a look at what we have in the denominator. This at the bottom here is 4 times w minus 4. This over here is 2 times w minus 4. So we're going to take we're going to take the highest degree of every factor. Well, w minus 4 is only listed to the first power, and we're just going to list that. So that's in common. And there's a 2 in here, but we're missing another 2 over here. So I'm going to multiply this by 2 again, top and bottom. Because this one's missing a 2 over here. So now the denominator is 4 times w minus 4. Same thing. Again, you notice I multiplied the top and the bottom by the same number. So it turns out that this one doesn't change on the left over here at all. And this one on the right, we're going to multiply w plus 4 times 2. W plus 4 times 2 is 2w plus 8. All right, now we have a common denominator. And I'm going to write it a single time here. I've got 4 times w minus 4. It's the same on both of these. 4 times w minus 4. And now we're going to add together the numerators here. I've gone ahead and multiplied both top and I've already multiplied that 2 in here. So now this is a good place to try to remember. This negative sign is applied to both terms on the top. And most of the time, this is where people make their errors. Is here, I'll make an error here. Minus 2w, and they'll go plus 8. No, it's not plus 8, because that negative sign is subtracting both of these things on the top. This is like a parenthesis, this line. So you have to distribute it in. So this should actually be 2w minus 8 when I distribute it in. So now my common denominator is still 4 times w minus 4. By the way, I'm not going to multiply it back out yet in case there's something else to do. So, and I get w minus 2w gives me a negative 1w plus 4. Okay? Now, you know, something we notice right here is that just in the last assignment we saw this as well, that this on the top is actually backwards from this. So if I pull out a negative out of this problem, pull a negative out, I'll end up with w minus 4. I just factored out a negative, and then it's like at the bottom here, but that's okay, I'm all done anyway. I pulled a negative out of this term here. I pulled it out of both of these, and I ended up with w minus 4. Now these two will cancel, and our final answer is negative 1 over 4. The process is the same. Factor them, come up with a common denominator by taking the highest degree of every base, but take it only once. And then go ahead and add together your numerators. Be on the lookout for distributing that negative in. That is the number one mistake that people make. All right, let's take a look at a little harder one. All right, we're going to deal with a complex fraction here now. It's got fractions within fractions. And but not everything's multiplied anymore, so we got more than just factors to worry about here. We need common denominators. Now, you notice I ran out of room on the next problem almost at the end there. We're going to probably have to use a lot of paper to do a problem like this. It gets pretty lengthy, so I'll probably have to move my answer to the top here, and if you need to come back and rewind to see how that's done. Now, the book does it a little differently than I'm going to do it here, but I want to do it this way because I find that it tends to be a little bit faster. I'm going to look at all of the denominators here. Now, I don't see this denominator here, but this is really 1 over 1, right? 1 is the same as 1 over 1. I'm going to look at all of the denominators and get all of the denominators to be the same in every place, okay? Well, this is missing a y, and this is missing an x, and this one's missing a y, and this is missing both x and y. So my common denominator here is going to have to be xy, x times y. Notice I made all the denominators the same. Okay? All right. To get from here to here, I had to multiply the bottom by y, so we're going to multiply the top by y. To get from here to here, we had to multiply the bottom by x, so I'm multiplying the top by x. To get from here to here, I had to multiply the bottom by xy, so I'm multiplying the top by xy. And that makes sense. xy over xy is 1, which is what we had originally. And to get from here to here, I had to multiply the bottom by y, so I have to multiply the top by y. There it is. Now, we can combine these terms now because we have all common denominators. So on the top, I'm going to have a denominator of xy, and on the bottom, I'm going to have a denominator of xy. On the top, I got y minus x, and on the bottom, I've got xy plus y. Now notice what I did is I added the numerators here. Y minus x is right here, and xy plus y. So I've rewritten this with the new denominators. Now something interesting is going to happen here, and the book does it a little differently, but I like doing it this way. Isn't it true that a complex fraction, I'm going to have to take this and flip it over and multiply up here? So I flipped this fraction over and multiplied, right? This is now moved up to the top here, and it's been flipped over because the line that said divide here, keep, change to multiply, and flip over. Keep, change, flip. We're going to flip this fraction over and put it up here. So this is now gone. It's not here any longer. And notice what happens here in the numerator, up here. These xy's are going to cancel, and I end up with y minus x on the top, right here, and xy plus y on the bottom. xy plus y is on the bottom. Now I could probably pull out a y here, but it's not going to help me factor this anymore. So there's my answer. Now your book does it a little differently. Sometimes they will just go ahead, keep, change, flip. They'll keep, change, flip anyway, and the denominators will end up doing a little canceling. But my entire denominators went out because I made them exactly the same. These complex fractions take a little practice. You'll have to work on those a little bit. Let's try another one in a story problem. All right, here's a problem that comes up every once in a while. We're asked to find the slope of something, but they're not going to give us all numbers here. We got some variables involved as well. Now if you remember, that slope is always taking the change in y over the change in x. So we're going to subtract the y coordinates and put it over a subtraction of the x coordinates. And you can see that we're going to create a complex fraction here. So let's take it doesn't matter the order we do these in, so I'm going to go y minus y over x minus x. Again, y minus y over x minus x. And we've created a complex fraction here. So let's do it just like we did the last one. Well, what's the common denominator got to be? Well, I see that p's got to be in the denominator, and so does 3 and 2, so 6 would have to be in the denominator. So my denominators are all going to be 6p. Okay, if the denominators are all 6p, then what did I have to do to get from here to here? Well, I had to multiply the bottom times 3p times 3p, so the top has to get multiplied times 3p. And you can see if I reduce that, I get a half, and that's right. Here I had to multiply the fraction by 6, just 6. 3 times 6 is going to be 18. 18 over 6 is 3, that's right, and there's still a p on the bottom, okay. To get from here to here, I had to multiply the bottom by 6 as well, so times 6. So this gives me 12. 12 over 6 is the 2, that's right. And to get from here to here, I had to multiply times 2p. Okay? 3 times 2p is 6p, so this is now 2p. So if we use the same principle in the last problem that we did before, if the denominators are the same, I end up with, let's go over here, I end up with 3p minus 18 over 6p and 12 minus 2p over 6p. Well, if I change flip here, and I keep this one, change to multiply, and flip this one over, I end up getting rid of the 6p's. They end up canceling, just like they did in the last problem. And I have 3p minus 18 over 12 minus 2p. Now I'm out of room here, but let's just go ahead and stick that up the top up here. Okay, I'm finding the slope, right? So I had 3p minus 18 over 12 minus 2p. Now what happened to the 6p's? Well, they canceled because when I flipped this fraction over, put it right up here, when I flipped that fraction over, right here, this went up here, 6p was on the top, 12 minus 2p was on the bottom, and the 6p's canceled one another. Okay, now I think I can simplify this a little bit. Let's take a 3 out of the top, and we get p minus 6. And if I take a 2 out of the bottom, I get 6 minus p. Okay. Well, there's that situation again where if I multiply, let's say I factor a -1 out of that. We're running out of room here again, aren't we? You're going to need a lot of paper. Let's take a -1 out of that bottom, out of the top one. Let's take a -1 out of the top one. I just rewrote it so they look the same. 6 minus p is the same as -p plus 6. I took a -1 out of the top because now I wanted to get these two the same. So when I cancel here, my answer is a -3 over 2. My slope is a -3 over 2. Now, there's a lot of paper involved in doing this. If you need to back up and watch that one again, you can. Slope turns out to be quite simple, -3 over 2. All right, well that's all the new information that I can provide for you today on doing these problems. I'm going to let you practice this 2 days. The first day you're going to have mostly odd problems. You can check those in the back of the book. Go back and watch this video a second time if you are not ready to do R. Watch it again after you practice Q. Come back and maybe watch it again, and so you're ready to do R. Let's do both assignments. If you got a question, send an email to me. Let me know if you have a question. I'll talk you through the problem either on an email, or I'll give you a call, or we can make a video for it if you need to. So enjoy that time together. This is frankly the hardest section in the entire chapter. We've got a lot in here. Make sure you do this because we're going to move on to talking about the graphs next time. All right. Take care.